Today we'll be doing the sum from 0 to infinity of 1 divided by 2k plus 1 quantity squared. And to start off, we'll recall an identity. So we're going to have gamma x times gamma 1 minus x is equal to pi cosecant of pi x. And from here, we'll take the natural log on both sides. So I have the natural log of gamma x times gamma 1 minus x is equal to the natural log of pi times cosecant of pi x. And using the property of logarithms, we're going to have a natural log of gamma x plus the natural log of gamma 1 minus x is the natural log of pi plus the natural log of cosecant of pi x. Differentiating both sides with respect to x, we're going to have gamma prime x over gamma x. We're going to have a plus gamma prime 1 minus x divided by gamma 1 minus x. But by the chain rule, we're going to have an extra negative here. The derivative constant is 0, plus this derivative will be 1 over cosecant of pi x, and then the derivative cosecant of pi x. So we're going to have a negative cosecant of pi x, cotangent of pi x, and by the chain rule, we're going to have an extra pi. So as you can see, these cosecant pi x end up canceling, and we'll also use the fact that the derivative of the natural log of gamma x is equal to, well, it's just going to be gamma prime x over gamma x. But this is equal to the digamma function, so digamma x. So using this, we have digamma x minus digamma 1 minus x is equal to negative pi cotangent of pi x. And then from here, multiplying a negative on both sides, we're going to have digamma 1 minus x minus digamma x is equal to pi cotangent of pi x. And so this identity here is the digamma reflection formula. So now that we have this result, we're going to differentiate both sides again. So now we'll also use the fact that the derivative of the digamma function is the trigamma function. So differentiating both sides here, it's going to yield negative trigamma 1 minus x minus trigamma x is equal to pi. The derivative cotangent will be a negative cosecant squared of pi x, and we're going to have an extra pi left over, so we're going to have a pi squared term. And I could factor out a negative, so we have a negative trigamma 1 minus x plus trigamma of x is equal to negative pi squared cosecant squared of pi x. So we could get rid of that. And now we have that trigamma 1 minus x plus trigamma x is equal to pi squared cosecant squared of pi x. And then from here, we use another fact that trigamma of x has the following series representation. We have the sum from 0 to infinity of 1 over k plus x quantity squared. So from here, we're going to let x equal 1/2. So we're going to have trigamma of 1/2 is the sum from 0 to infinity 1 over k plus 1/2 quantity squared. We can rewrite this as the sum from 0 to infinity 1 over 2k plus 1 quantity squared, and we're going to have a 2 squared, but that's going to be a 4. So we're going to have 4 times the sum from 0 to infinity of 1 over 2k plus 1 squared. But this sum is the sum we're actually looking for. So multiplying 1/4 on both sides, we have 1/4 times trigamma of 1/2 is equal to the sum from 0 to infinity of 1 divided by 2k plus 1 quantity squared. And we'll go back to this identity. So let's write it again. So we have trigamma of 1 minus x plus trigamma x is equal to pi squared cosecant squared of pi x. So from here, we're going to do the same thing. We're going to let x equal 1/2. So we have trigamma of 1 minus 1/2 plus trigamma of 1/2 is equal to pi squared cosecant of pi over 2 squared. But then we're just going to have a trigamma of 1/2 plus trigamma of 1/2 is pi squared cosecant of pi over 2 is 1, and 1 squared is 1. So this means that we have twice trigamma of 1/2 is equal to pi squared. And solving for trigamma of 1/2, we have trigamma of 1/2 is equal to pi squared over 2. But we said that 1/4 trigamma of 1/2 is the desired sum, the sum from 0 to infinity, 1 divided by 2k plus 1 quantity squared. So this means that the sum from 0 to infinity, 1 divided by 2k plus 1 squared is equal to 1/4 times pi squared over 2, which is equal to pi squared over 8. And so that is the final result. Thank you very much for watching.